Hey there, grade 12s. Last recording in this unit regarding energy changes and rates. So we'll go through the reaction mechanisms lesson, and what a mechanism is just the way that a reaction happens. So we'll jump right into it. So what we're going to look to define here are a couple of terms right off the bat: an elementary process, a reaction mechanism, an intermediate, and a rate determining step, which, as you can imagine, it's a step in a reaction that determines the rate. Once we're able to do that, we'll look at what a mechanism is and how they're suggested, how they can change and how they're not fixed for a given reaction. And then we'll be able to explain the properties of a mechanism and if it's suitable with the theory that we understand about reactions. And then we'll apply this to potential energy diagrams. So we'll start off the bat with some terms. All right, just like when a car is being built, it's not just built all together. We don't take tires, an engine, and a car and just put them on top of each other. Each step happens in a certain order to get a final product. And a reaction is the same. We don't just mix reactants together and they turn into products magically. There's certain steps that happen. Atoms need to rearrange in certain orders. Products need to be in certain orientations. And the sequence or the order of all of these steps is called the reaction mechanism. So you can think of a list of steps for a recipe, for example. You have 1, 2, 3, 4, and so on. Each one of those steps is known as an elementary process in a chemical reaction. The collection of all the steps is known as the mechanism of the reaction, or reaction mechanism. So now that those are clear, we'll be able to move on going forward. So when we're analyzing reaction mechanisms, there's three things we need to consider. The probability of a reaction, which means there's no more than 3 reactants that occur. All of each of the steps need to add up to the overall equation. All right, example there, if we're building a car and we have computer parts, that's not going to help us in our overall goal. So if we have reactants that don't actually contribute to the final products, then it's not going to be much help for us either. Finally, the slowest step, which is called the rate determining step, or RDS as we'll use here, is what we use to determine the rate law. And it has to be consistent with the experimentally determined rate law. So there's a theoretical side to this and an empirical data side. So we'll examine each of those 3 postulates in a little more detail here. So number 1, each elementary reaction must involve no more than 3 reactant molecules, and that has to do with probability. The more molecules that are involved, the less likely the reaction is to occur. And you can ask yourself, for these 2 examples down here, A and B. In reaction A, we have 2 molecules. In reaction B, we have 5 molecules that are reacting. Right, we'll just make that clear right here. So how did we determine that? Well, there are 2 different substances in reaction A, and there's 1 of each. In reaction B, there's 4 of one reactant and 5 of another. So what that means is all 5 of those molecules need to collide at the same time with the proper amount of energy to react. That's a very low probability compared to 2 molecules reacting. So what we say is, for an elementary step in one of those individual parts of a process, we look for anything with 3 or less. And even 3 is pushing it, but it's generally considered acceptable from that point of view. A 5-molecule reaction is very unlikely, and it will happen in smaller elementary processes. Reaction A is likely to occur in 1 step. Reaction B is unlikely to occur in 1 step. So the second postulate of a mechanism is that all the individual steps need to add up to the overall reaction. So we'll draw a line here just to separate these. And you can see here, this was that reaction from example B on the slide before. All right, the 4 hydrogen bromides reacting with the oxygen. And we said it's unlikely because there's 5 molecules. So what's more likely to happen are these steps, 1, 2, and 3 that you see below it. Now you've got some data on the speed. We'll talk about that in a second. But the idea is that each one of those steps, which is, again, they're proposed. It doesn't mean it has to happen like this. This is just one way it can happen. Right? Each of those steps carries out a smaller process that contributes to the overall process. And what happens is the products of one reaction become the reactants in the next. So the product in reactant 1 is the reactant in reaction 2. The product in reaction 2 becomes the reactant in product in reaction 3. Right? So those are called reaction intermediates, which is at the bottom here. Right? When something's formed by a certain reaction and then it gets used up in another step. So we've talked about adding reactions before, and it's the idea that we put all of the reactants on one side and all of the products on another, and then we cancel out and simplify. So just like you would treat variables similarly, right? If I had x plus y equals 2 take away z, and then I had 2x take away 2y equals 5 plus 2z. We know to add those two equations, we add the left sides and the right sides to make them equal to each other. So that's just a little review of that there. We do the exact same thing with chemical reactions. And to make it easy, for elementary steps, we look at the products and the reactants. So because product 1 appears as reactant number 2, they cancel each other out. So if we were to write all the reactants on one side and all the products on another, we would find that that's a common term. Now, what you notice here is that this 2 in front of the brackets means that this reaction number 3 happens 2 times. It can't happen in one step because then there'd be 4 molecules reacting, 2 of the first and 2 of the second reactant. Right? 2 of that plus 2 of that would be 4 molecules, which is too complex to be an elementary step. So instead, 1 reacts with 1, and then that reaction happens again as a separate reaction. Right? If all 4 of them reacted together, you wouldn't get these products. You would have something else. Okay, so the 2 with brackets in front of a reaction means that it happens twice, making it a valid elementary step. So these 2 get canceled out by that there because it's multiplied by 2. And when we add everything up, all the reactants add up to 4 HBr. Can circle 1, 2, 3, and 4 because the reaction happens twice. There's 1 oxygen, 2 water here because the reaction happened twice, and same with the bromine. Okay, so all of the reactants and all of the products added up and simplified give us the overall reaction. Finally, the slowest step, and that's where that speed data comes from in the previous slide, has to be consistent with the experimentally determined rate law. So you would need data to determine this, either the rate law itself or some kind of information. So remember, the rate law just tells us the rate law. Sorry, it's not an integrated rate law where we have a change over time. This is where we have the rate proportional to the concentrations of the reactants. Okay. So if we look at that rate law that we see there, what we're looking at is the slowest step, right? And the reason for that is that limits how fast the reaction can go. And we look at the slowest step because the other steps can be considered almost instantaneous. The rest of the rate depends on that slowest step, and it holds back the other processes from going forward. So the reactants here are similar, and this is a coincidence, but they're similar to the overall reaction, right, where we have HBr and O2, right? And experimentally, the rate law is determined to be that, but each with an exponent of 1. Okay, so we're not showing the data here, we're just being told what it actually is. And empirically means with a controlled experiment. So the data has been collected, analyzed, and averaged to figure that out. So with elementary steps, the key here is the coefficients become the exponents on the in the rate law, sorry. Right? And that's true only for elementary steps. If it's an overall reaction with more than 5 molecules, this does not hold true. Then we need data to determine what that is, and you can review that in our previous lesson on the rate law. Okay. So a couple of notes before we move forward with some examples. Mechanisms are proposed. It doesn't mean that that's how they happen. It's just one possible outcome, so you can suggest more than one mechanism as long as it follows the 3 rules above. They can't be observed or detected because they're so quick, so we can't actually pause a reaction and measure the formation of something. And they have to be based on some measurable fact, using some kind of theory that we've talked about before. So we'll take a look at an example here, and this is the example we've been looking at so far. So the proposed mechanism is the steps 1, 2, and we said step 3 happens twice, so we'll call it 3A and 3B. Right? So if we consider the rules that we talked about, we had rule 1, rule 2, and rule 3. We'll just make a little checklist. For rule 1, we said each step should have less than 3 molecules. So we'll say this. Less than or equal to 3. So if we do a quick little checklist, there's 2 in the first, 2 in the second, 2 in the third, and 2 in the fourth. So we're okay there. Now, the second step. All the steps must add to target equation. Right, and just making some small notes here. So if we cancel out all the reaction intermediates in this case, 2 of those, right, we can see that there's 1, 2, 3, 4 hydrogen bromides. There's 1 oxygen. There are 2 waters on the product side, and there are 2 bromines on the product side as well. So all of the steps add up to the overall reaction, and everything that's not there is canceled out. Finally, the slowest step is the rate determining step. So we were told previously that the first step is the slowest, which makes the rest faster. So they'll just be annotated as fast. Now, how can we verify that? Well, if we look at the potential energy diagram, there's a couple of things we'll notice. The slowest step has the highest activation energy of any step. So in this case, yes, the slowest step agrees. Right? Rate determining step tells us what the rate law is. So looking at the data on the graph, that can be determined with numbers or by looking at the activation energy. Excuse me. So if we look at the activation energy, it's from the reactants to the activated complex, right? And each peak represents a new activated complex. Right? So what that means is the number of peaks tells us the number of elementary steps in the reaction. So because there's 3 here, that means there are 3 different steps. But number 3 happens twice. It doesn't change the energy profile, it just means that it happens again. So, going forward from there, the highest activation energy, which is from reactants to activated complex each time, gives us the slowest step, and in this case it's step number 1. So this profile fits based on the data that we see. And that's what we use mechanisms for, to verify. We look at the rules, what's proposed, and see if they match up with each other. So in our example here, right, we're asked to propose a mechanism based on this profile. So right off the bat, we're being told that this happens in more than one step. So what we want to know is how many steps. And remember, we call those elementary steps. So to determine that, the number of peaks, in this case it's 2, means that there's 2 steps. Right? So we have reaction 1 and reaction 2. Now if you'd like to pause and try to determine what the products and reactants are, it's based on each individual steps, go ahead. And if you're a little confused, we'll explain that here. So if you've paused, hopefully we'll be able to check your work now. So the reactants of the first reaction are simple. They are the reactants that first show up on the graph. So in this case, it will be hydrogen plus 2 iodine chloride. And now we're looking for the products. So the way that we determine the products of the elementary steps is based on the valleys. Okay. So the valley in each diagram represents the products of a step and the reactants of the next step, because you can see it bottoms out and then they become reactants again. So we have HCl plus HI plus ICl, and you can see that we use Times New Roman font I just so we can see the difference between the L and it. Now, those, because they're at the bottom of the valley and then they become a new transition state here, mean that they're the next reactants. Right? So the hydrochloric acid plus the hydrogen iodide here produce the products that we see at the bottom, which are just the two listed there. So we've got iodine plus hydrogen chloride. And then from here, this is an acceptable mechanism because the products cancel out with the reactants and they add up to the target equation, and no other I forgot what I was going to say there. Oh, and neither of the reactions have more than 3 reactants, so it's acceptable there. Now, if we had to determine which one of those steps was slowest, right, you can pause and try to figure that out for a second. Okay, and if you've paused, welcome back. You'll notice that it's the one with the largest activation energy, which is the first reactant, which makes the second one faster, so we just annotate it as fast. Okay, so hopefully that helps clear up what the mechanism is, how it can be proposed, and this is the kind of data that we would need. So, to predict the rate law, right, and remember the rate law is defined as R equals K times the concentration of the reactants to some exponent. Right? We can only use this method for elementary processes. Keep that in mind. Okay, and those are reactions that follow all the previous rules. So if we don't know if it's an elementary process or if it has more than 3 molecules, we can't use this method. So keep that in mind. This doesn't apply to everything. In the rate law, the coefficients are the exponents. And it's that simple, only for elementary processes. So in this case, if we look at the reaction here that we're given, NaCl plus Cl, we know the rate law is based on the reactants. So reactant 1 is NaCl and reactant 2 is Cl. And what we're saying is that for an elementary process, the exponents are the coefficients. So there's our rate law. And what does that mean? Well, they're both first order. So that means if NaCl doubles, the rate doubles. And you can refer back to our last recording for that, but it was the change in factor of the concentration to some exponent is equal to the factor that the rate changes by. And if it's a first order reaction, then that means whatever the concentration changes by, the rate changes by. So that means the same for chlorine as well. In this case, they'll have the same factor. So looking at this process here, if we try to determine what the rate law is, we're told that it is an elementary process. So the reactant, there's only one, is related to the rate, NO2, and in this case it's to the exponent of 2. Right? Now we always use the rate determining step, or the slow step, right, to determine what this is. So in a list of mechanisms, we look for the one that's the slowest, and that's what we develop this. So in this list, that has to be beside that for us to determine the rate law with it. So let's look at one final example. We'll look at fictitious molecules here. You can see 3 elementary steps in this mechanism. Write the overall equation. So again, pause these examples and try them yourself. Right? And if you've paused, what we're looking is to cancel out the intermediates. So that product shows up in that reaction, and that product shows up in that reaction. Right? So those cancel out, and we put all of the reactants together. In this case, there's going to be 2 of the Z's plus 2 of the Y's, producing XY2, Z2. So that's our target equation. Now, if we were to propose a rate law, again, it has to be based on the slowest step. So R is equal to K times Y to the exponent of 2 times the concentration of molecule Z. Okay, and again, for elementary steps, the coefficients become the exponents of the slowest step, which is called the rate determining step. So to follow up with that, we're told that in this reaction, the rate law is proposed as this. Is it possible? All right, so looking at this, if you look at this reaction, and we're told that it's an overall reaction, right? We're not told what the elementary steps are, but we're told that the rate is based on this formula here. So the important part is the rate law won't always match the overall equation. So hopefully you've paused this and had a chance to try it yourself. Yes, it's possible. Possible doesn't mean it always will be. And we can say that the rate law won't always match. Right? And that's because the slowest step doesn't have the same reactants as the overall equation. So if we were to break this down, two A's or an A2, a diatomic molecule, combines with two single B elements to form molecule AB. So for that to happen, really, what we have is this. Two A's bonded together, and then element B separately combining to form two ABs. So if we look at that, really, logically, what needs to happen is these need to split up and then react with B separately. So we can propose the mechanisms for that and say, step 1 involves molecule A splitting into single atoms, and then step 2 involves those atoms combining with the molecules B to form 2AB. Now, the problem with that is there's 4 molecules. So what we could do is we can rewrite that. 2 of that equation will happen. We can just factor out the 2 here. Right, so what we've done is propose an acceptable mechanism. And if we look at step 1, right, the rate law would be based on this. Because if we rewrite it, it's based on the reactants to their exponent, which is just 1 in this case. So that would make step 1 the slowest and step 2 the faster one. Right, so a little bit of logic and reasoning involved, but it is possible. So there's some homework questions along with the end of unit review. Hopefully this helped clear it up. Feel free to go back and watch the examples if there's something you need cleared up, and good luck with the studying.